And we're live.
Lesson 1, momentum and impulse. Momentum is a fancy physics word. It also means something in English. We talk about sports teams having momentum. In physics, it's the amount of motion an object has. It's how much motion an object possesses. And it turns out the amount of motion an object possesses depends on two things. I wrote here, for each of the diagrams below, state whether the amount of motion is comparatively large or small. So we have 4 situations. I only see 3. We're going to draw a 4th. The first situation is small mass going slow. Second situation is small mass going fast. Third situation is big mass going slow. The worst situation is big mass going really fast. Let's talk about these. Small mass moving slow, small mass ping pong ball moving slow, tossed underhand. If that hit you in the face, Shaq, would it do much damage? Small amount of motion, small amount of momentum. What about a small mass moving really fast? Bullet. If that hit you, would that be a pleasant experience? What about a big mass moving slow? So what if instead of lobbing a ping pong ball underhand towards you, what if I lobbed a bowling ball underhand towards you and it hit you in the face? Thumbs up or thumbs down? Would you want a bowling ball even traveling slowly? You know what? Okay. The worst situations are a heavy mass moving really fast, like what? Meteor, car, locomotive. Really has a lot of mass. You'll look at later the Twin Towers when they came down. Those jets had a great deal of momentum, big mass, moving real fast. Momentum had to go somewhere. It's not some government conspiracy. The buildings came down because they were unable to absorb the momentum. You know what? Another common everyday that you've read about, which is why it was used in this manner, was a cannonball. Would be a good example. Explain your answer. Momentum depends on, from these 4 examples, what 2 things do you think momentum depends on? An object's what and an object's what? Ooh, she used physics words. By the way, size would imply volume. No, because a balloon has a lot of volume. But I'm happy to have that hit me in the face, right? You guys can go. Thank you. Yeah. Now, what letter does momentum begin with? M's already taken. What does M stand for in our physics world? Well, meters is a unit, but as a variable, when I say F equals ma, what's the M? Mass. So we need something else for momentum. It turns out momentum is equal to mass times velocity. It's a product. It's the motion product. And so we use the letter P for momentum. Okay? Momentum is mass times velocity. And it's a vector. You'll notice I'm being very careful with my vector notations. That's going to be really, really important. If you see there's a change in direction, you better let one way be positive and you better let the other way be negative. What would the units be? Well, what do I measure mass in? Kilograms. What do I measure velocity in? And the units for momentum are kilogram meters per second. They haven't shortened it and given it a name. There is a movement afoot right now to rename that one Einstein, because he doesn't have a unit named after him, and he probably should. It may happen in your lifetime, so it may be The same way, for the longest time, force was measured in kilogram meters per second squared, mass times acceleration. And then finally, the international body that governs units, we'll call that a Newton. We'll give it a name. The same way energy was measured for the longest time in Newton meters, and then someone came along and the committee said, let's give it a name, call it a joule. They may name this in Einstein. Hasn't happened yet. So for now, kilogram meters per second. Not to be confused with, that's a force, because that's mass times acceleration. There is another way. It turns out another unit is a Newton second. That's also another way to measure momentum. Really? Yep. Because Newton, well, what does Newton measure? Force. Force F equals what? MA. Newton is really kilogram meters per second squared. Can you see the MA? So a Newton second would be that times 1 second. How many S's are there on top? 1. How many S's in the bottom of the fraction? 2. One of the S's is going to cancel, and lo and behold, what's left behind? Kilogram meter per second. I tend to use this one whenever I'm going mass times velocity because it's easy to remember. Mass, kilogram, velocity, meters per second. That's the units. But for what it's worth, you'll see some textbooks talk about Newton seconds as a measure of momentum. So whenever I introduce a new concept, Emma, I like to try and give you a gut instinct for what's really big and what's really small. So I've got some momenta is the plural, to kind of think about and analyze. So I want to estimate the momentum of a top pitcher's fastball, the momentum of a bike and rider, and the momentum of a car. Who are my baseball players? What's a baseball weigh in grams? Let's make a reasonable guess. Does a baseball weigh a kilogram? Does a baseball weigh a pound? So less than a kilogram, less than a pound. Does a baseball weigh about half a pound? You know what? My gut is a baseball weighs around... Oh, change colors, Mr. D. Maybe 250, maybe 150, but I bet you I'm close. I don't think it's 800. I don't think it's anywhere close to a kilogram. In fact, I don't even think it's close to half a kilogram. But I need to change this from grams to kilograms, so about 0.2. A major league pitcher, what's their speed? And you can give it to me in miles per hour because we can do a conversion. What's a major league professional pitcher? What do the top guys max out at? What's a nice round number really close to that we'll do the math with? So you know what? Let's say the speed is 100 miles per hour. Now, there's a trick to go from miles per hour to meters per second. It's divide by 2 and make it a little smaller. 100 divided by 2 is what in your head? 50. A nice round number, a little smaller than that, 45. 100 miles per hour is around 45 meters per second, roughly. I'm off by a bit, but I'm close. So momentum is going to be mass times velocity, 0.2 times 45. 9? Double check me. Yeah? If you got hit by a baseball, would it hurt? By a major league fastball, would it hurt? If it didn't hit you in the head, would it kill you? So you know what? Trying to absorb 9 or, 10 kilogram meters per second. Ouch. But you're probably just going to have a big bruise. Probably not going to break a bone. I know it can if it hits you right on the knuckle, and okay, but probably not. Certainly, as long as it hit you in the head, you're walking away. Bike and rider. What would be a good estimate for the mass of a bike and rider together? $10? No. kilograms. What do you think? We're being rough. 50? I know 50, I know if you go times by 2.2, that's pounds. That would be about a 130-pound, 140-pound person. That's on the light side. Add the bike. So I want a nice round number, a little bit bigger than 50. Someone said 80. Sure, you know, I'll go 75. Okay, what about the speed of a biker? Can a biker go 60 kilometers per hour? Can you do city speed with the cars for an extended period of time? No? Okay. Could you go 40 kilometers per hour? I think so. School zone speed? Sure. You know what? I'm going to be clever. I'm going to pick a nice number really close to 40 kilometers per hour. I'm going to say why did I pick 36? Because to go from kilometers per hour to meters per second, what do we divide by? Ah, see how clever that was? So divide by 3.6, and that's going to give us 10 meters per second. Ben, really? It's 75 times 10. You reached for your calculator? Really? Ben, in your head, without a calculator, what's the momentum of this? What is it? 750. Thank you, my friend. By the way, I always set some. I'm watching for the first person who flinches. You were the first one to jump. You probably weren't going to need a calculator after all. You know what, Ben? Roughly 1,000. Roughly, in other words, 10 baseball. Bike, about 1,000-ish. If you were walking and you got hit by a bicyclist at full sprint speed, would you die? Would you probably break bones? So I'm going to say, you know what, 1,000 kilogram meters per second. Injury. Ouch, baseball. Say a few bad words, but you'll be better in a couple of days. Hit by a bike, yeah, you probably break a bone or two, crack your ribs. Probably have to go to the hospital, but you probably might not even be needing to call an ambulance. It would probably be, you know, you got a car, let me get in, take me to the hospital because something feels wrong. Car. What's a good mass for a car? 1,000? Sure. Some are heavier. Somebody says 1,000 or what? I think that's a little heavy. I think 3,000 kilograms. Pounds, you're okay. I think 3,000 kilograms is a little heavy. I'm going to say a nice round number of 1,000. And you know what? Let's put this car on the freeway. Not on the highway, on the freeway. What's the speed limit on the freeway? It's also a nice round number. 100. So you know what? Let's go V equals, now that's kilometers per hour, so let's divide by 3.6. What's the speed in meters per second? This one you can use a calculator for. 27.8. You know what? I'm going to say approximately 30 meters per second. We're being very rough. In your head, without a calculator, what's the momentum of a car? Right? Probably. Absorbing 30,000 kilogram meters per second all at once, Manny, probably not going to happen. Absorbing 1,000 kilogram meters per second all at once, most of us could pull it off, but it wouldn't be pleasant. Absorbing 9 kilogram meters per second, bring it on. It's going to hurt. But as long as you don't hit me anywhere special, like in my temple, in my head, I'm probably going to be okay. Right? Oh, you know what? I did Google the mass of a baseball. Nobody bothered looking down at the next question? Apparently a baseball has a mass of 0.14 kilograms. It's moving at 35 meters per second, about 70 miles an hour. This is a change-up or a slow pitch. Okay? A says, find the momentum of the baseball. So our new equation, momentum equals mass times velocity. Really, Rob, I should have said find the magnitude of the momentum, because since momentum is a vector, I don't have enough to give you a direction. But, okay, fair enough. Hey, Rob, what's the mass? Yep. What's the speed or velocity? You can use your... Wait a minute. I think I can do this in my head. Because 14 is 2 times 7, and 35 is 5 times 7, so there's a 2 and a 5. That's a 10, 7... it's 49 times 10 with 2 decimal. 4.9? Yeah. Units. Kilogram meters per second. About half of the fastball that we looked at earlier. This one, if you got hit, you'd be sore and you'd probably be choked. But it probably wouldn't even break a knuckle if it hit you right on the knuckle. B says, find the velocity at which a bowling ball, which has a mass of 7.26 kilograms, would have the same momentum as the baseball. What are they asking you to find in part B? Well, they gave me momentum. They gave me mass. All right. New equation. I'm not going to bother writing this on your formula sheet. Kai, get the V by itself. Yeah, okay. Apparently, another equation for velocity, of which we've got like 9 or 10 now, apparently is, hey, if you know the momentum and you divide by the mass, you've got the velocity. So it's going to be 4.9 from part A, 7.26. Okay. Getting hit by a slow pitch in baseball is like getting hit by a bowling ball at 0.675 meters per second. Is that right? Okay. What's momentum, Emma? How much motion an object has, and you can calculate it by going mass times velocity. Faster it is, the bigger it is, the more mass it has, the more damage it's going to do. That's why you'll often see if a locomotive hits a car, you've seen it in the movies, the car gets demolished and the locomotive, what? Hardly even slows down, right? Example 3. I wrote, prove that momentum change equals mass times velocity change. Note, change in anything equal, what's change in anything always going to be worth memorizing, by the way? Yeah. Didn't even need a calculator for that. Shut up, Mr. Dueck. Sorry. So I guess, Ben, momentum change, and our symbol for change in is that lovely delta, is going to be final minus initial. True? Let's break this down further. What is momentum? What is the equation? Momentum is what times what? What's our new equation? Mass times velocity, so I guess momentum final is going to be mass v final, and I guess momentum initial is going to be mass v initial, because I don't think the mass of the object is changing. Its speed is changing. Baseball doesn't become lighter on its way to the plate. McKinley, can you read to me the right-hand side of this new equation? Change in momentum equals
mv final minus mv.
Did you say m twice? You're saying there's an m in everything? We can do something when there's a term in everything. We can pull out a math skill that has a 3-letter acronym that begins with the letter G. Yeah. Who said it? What was it? You must have had a good Math 10 teacher who told you to always. Okay. There's a GCF of m. Okay. Well, if I factor that out, I'm going to get m bracket v final minus v initial. And Anthony, while you're on a roll, look at the bracket. What is final minus initial? Change in. Okay? In other words, if change in anything is final minus initial, then final minus initial must be change in anything. Change in what? Velocity. I can actually then say, okay, change in momentum can be written as m change in velocity, which, call me silly, I think it's what I was trying to prove. It said, prove that momentum change, the left-hand side, equals mass times velocity change. I just did. Having said that, Jeff, I don't actually use that last one all that often. I use it once in a blue moon. The one that I use, the two that I use the most, if they start talking about change in momentum, I'm almost always thinking, oh, that's going to be mv final minus mv initial. Or that's going to be m bracket v final minus v initial, close bracket. I'll be honest, it's that top one of those two that I, by far, use the most. So change in momentum, you can find it by going mass times velocity change. We're very interested in change in momentum. In fact, we have another name for it. Impulse. Impulse is defined as change in momentum. Halen, what's another word for impulse?
Change in momentum.
Emma, what's another word for impulse? Nice and loud with authority. What's another word for impulse? Manny, what's another word for impulse? Ready, Trish? What's another word for change in momentum? Impulse. When I say impulse, you think knock, knock. Impulse. And you're going to say?
Change in momentum.
Okay. They're interchangeable. And the reason I'm emphasizing that so much is every year in this unit, I do a question on the test where I say, find the change in momentum. And Kyle gets it right. And then the next question says, find the impulse, and he leaves it blank. Because he's forgotten that impulse is interchangeable to change in momentum. Oh, and Anthony, what's change in anything? In other words, if I say find the impulse, what I'm really saying is find the final momentum minus, find the initial momentum. Final minus initial. Impulse is change in momentum. Change in momentum is impulse. Those of you that are Star Trek fans, you may recall when you watch Star Trek, they'll talk about using the impulse engines. What are they saying? They're saying we're changing the momentum of our starship. And since momentum is mass times velocity, and they're not changing the ship's mass, they must be changing the ship's velocity. That's the fancy Star Trek-y term for speed up or slow down. Okay? Impulse. Change in momentum. And I can find it by going mass times change in velocity, or mv final minus mv initial. But there's also another way I can find it. And it's going to allow us to link two hugely important concepts together in one equation. It's going to allow us to also analyze car accidents. Example 4 says, fill in the steps below to find the impulse equation. And I wrote, take Newton's second law, F equals ma, and get the a by itself. So if F equals ma, what does a equal? Dane, my friend, if F equals ma, get the a by itself. I need to move the m over. How?
I'm going to say you're going to times it over.
What's the m doing to the a right now?
No, it's timesing, so you're getting to divide.
And you're going to say it with authority and confidence. One way to find acceleration is if I know the force, divide by the mass. Rob, we had another equation, actually with the very first one I think that we learned all year. VF equals VI plus AT. That has acceleration in it as well. How good you feeling? Can you get the A by itself in that one?
Yeah.
Go for it.
You have to times the A over.
Leave the A where it is. Move the other stuff over. So leave the VF. What are you going to do with the VI?
And times it over.
Is it timesing the A?
Oh, no, it's minus over.
So it's going to be VF.
And then you divide by the T.
Remember that, right? Coming back. This is also good review because we're nearly towards the end of the year. Okay. Dane, can you read me the top equation? Yours, A equals what?
Sorry.
It's okay.
Read my notes.
A equals?
A equals F over M.
Good. Rob, can you read me your equation? A equals?
A equals V final minus V initial over divided by time.
So yours equals acceleration, and yours equals acceleration. Then what can we say? They equal each other. Okay? We can now say, hey, that must mean that F over M is the same as VF minus VI over T. You okay with that, Kurt? I don't like the fractions. I'm going to cross multiply to get rid of fractions. I'm going to times the M over to this side. I'm going to times the T over to this side. And what I'm going to end up with is this. Force times time equals M bracket VF minus VI. By the way, from the top of the page, what is M bracket VF minus VI the same as? Oh, and what's another word for change in momentum? Turns out another way to calculate impulse is force times time, except look up, look up, look up, look up. Because there's a delta in front of the P, we put a delta in front of the T. We said at the very beginning of the year, time is always a change in, and we almost always just drop the delta because we're lazy. Here, to make it symmetrical, we say, well, since the right-hand side's a change in, I guess we should have the left-hand side be an obvious change in, too. This is our second big equation. Our first one was how we define momentum, mass times velocity. And then we said, oh, you know what? Impulse, which is change in momentum, can be thought of as final minus initial, but it can also be thought of as force times time. And think about this. We now have one equation that has on the left-hand side force, which you will agree has been a fairly key concept all year long, and on the right-hand side, velocity, which has also been a fairly key concept all year long. It's kind of nice. By the way, on the next page it says substitute the result, and I always forget that I included that, and I always do the substitute because I'm so excited to get here. I do it at the bottom of this page, so you can kind of say, we already did it. So here's what this says then. Force times change in time equals mass times change in velocity, or force times change in time equals change in momentum. Another word for which is impulse. By the way, Jeff, what do I measure force in? What are the units? Do you remember? Yes? What do I measure time in? And this is momentum. Stay on this page, you guys, but this is also another way to prove what I said at the bottom of this page. Another way to measure momentum is a Newton second, because you just told me it's force times time. So that equation that we just derived actually kind of pops out of those units, to be quite honest. Big deal. Oh, huge deal. Really, really, really handy. Okay. Oh, and by the way, one more thing. What's change in anything? The one I often use the most is force times change in time equals mv final minus mv initial. And then often I'll get the force by itself by dividing by t. or I'll get the time by itself by dividing by force. Because usually what I'm interested is either how hard the car hit the other car at, force, or, hey, how long did the car crash last? Time. Just because in a car crash, I usually know V final. What's V final in almost any car crash? 0. And usually V initial is, look at the speedometer, stupid, whatever. Anyways. You may have noticed, I wrote here, that we seem to vector notation. This is because there are vector problems that are often changes in direction. And a classic collision momentum example is hitting a baseball. Because I think a baseball comes in at one direction and leaves in the opposite direction. Now, you can hit a baseball at an angle, so it could come in straight at you, Halen, and could leave the bat at an angle like a pop fly. We do not have the physics to deal with that. So what we're going to say, we're going to assume, read along with me, it says a baseball is pitched horizontally at 38 meters per second. After it's hit by a bat, it moves horizontally at negative 55 meters per second. We're assuming the pitch came in as a line drive and left as a line drive to keep the physics nice. Why did I say the second velocity was negative? Opposite direction. This is important. Rebounds. Okay. Kurt, what does part A want me to find? Impulse. What's another word for impulse, boys and girls? Okay. Now, here's the problem. I have two equations for impulse. I have one that has a force and a time in it, and I have one that has masses and velocities in it. Which one will I use? Both. Which one will I use here? Go look at what they gave you. So I would look, do I see newtons anywhere in what they gave me? Do I see a force? No. Do I see seconds? Do I see a time anywhere in what they gave me? No. Do I see a mass and two different velocities? Then I think I'm going to use this one. Do you see how you can reason it out, Dane? Okay. Both are fair game. I may give you this same question, but instead of telling you how fast it came in and how fast it left at, I may tell you what the bat force was and how long the impact lasted for. Okay, then you'd use F delta T. Kurt, what's the mass? Curtis, what's the mass? Yep, it's there. Kilograms. What do we got? Yeah, sorry, too obvious. My bad. And then, okay, folks, V final. What's V final? Be a little bit careful here. What's the final? Huh? Negative. Pardon me? I could do this one here. I have learned over the years, Darren, and this tells you how nerdy and how lazy I am, when I actually, Darian, count up the number of calculator strokes, this has one or two more, because of the brackets, calculator strokes than going that times minus that times. Also, I'm much less likely to make a dumb mistake typing this one here than this one, so I tend to avoid this. The only time I would use this if they specifically said, find the change in velocity, then I would, okay, I guess I could better go final minus initial. But for now, I'm just going to go straight plug and chug. So Darian minus the mass, again, is still 0.144 Darian. What's V initial? .38, right? The incoming. What's the impulse that the bat has to deliver to the baseball? What's the change in momentum that this baseball undergoes? I get negative 13.4. What's the negative saying in the opposite direction that it was coming in? So whichever way it was coming in, because I called that positive, it's saying, oh, look. So let's suppose the baseball was coming in to your right, my left. It was coming in this way. If I want to send it off backwards that way, I have to apply a change in momentum in this direction because the baseball bat has to first bring it to a stop and then continue applying a force in that direction. Negative 13.4 kilogram meters per second. You could also say Newton second, but I noticed since I went mass times velocity to find this, my tendency is to go right as my units, mass times velocity. Kyle, what's B want me to find? Force. What did I find in part A? It would be wonderful if there was an equation that had force and impulse in it. There is. Impulse is also force times change in time. Kyle, how would I get the force by itself? Did they give me the time in the question? They did? What's the time of impact? 0.8, careful, what? Milliseconds. We'll have to do a bit of a unit conversion. Suck it up. We can deal with it. Okay, so this is, I agree, the force is going to be the impulse divided by the time. I don't know if you remember way back when I did forces, we did Newton's laws. We said Newton's second law was F equals ma. And I said to you at that time, actually, that wasn't quite the equation the way he wrote it. This is how he wrote F equals ma. He was much more interested in momentum and time. We use F equals ma. We call that Newton's second law. But when he published it, his second law was F equals change momentum over time, for what it's worth. Ooh, I know the change in momentum. I'm going to write negative 13.4, but I'm going to use the 13.392 start on my calculator, divided by 0.8. What's milli? 10 to the what? I think it's on your formula sheet somewhere. 10 to the negative 3. So the force that this bat applies is the impulse divided by, bracket, 0.8 times 10 to the negative 3. It's kind of weird looking scientific notation. In fact, it's not technically correct scientific notation, but my calculator will handle it anyways, so what do I care? How many newtons of force? Negative, because it's in the opposite direction that the ball came in at, 16,700. Is that a big force? Would you want to be hit in the head with a baseball bat? No. Would it probably do damage? Might even be fatal, depending. C. C. Zach, what's part C you want me to find?
The average acceleration.
What did I find in part B?
The average force.
I'm wondering, also trying to teach you how to be good test writers. I wonder if there's an equation that has force and acceleration in it, because I usually think maybe I'll use part B to find part C. Is there an equation that has force and acceleration in it? Yeah. Hey, Zach, what's the equation that has force and acceleration in it? What is it, Zach? Really obvious. F equals? Yeah. M what? M what? Oh. There's the equation that has force and acceleration in it. Zach, recover. How would I get the A by itself? So the acceleration that this baseball is going to feel is going to be negative 16,740. I'll use the full value on my calculator. Divided by 0.144. This baseball really is going to accelerate pretty fast. Negative 116,250. I'll go to negative 116,000. I'll go to 3 sig figs. Negative 116,000. Units, Zach. It's acceleration. Impulse. change in momentum, and it can be found by actually going change in momentum, final minus initial, or it can be found by going force times time. Momentum can be used to analyze football, to explain a lot with football. So my football players, listen up. What's the momentum of a 112-kilogram football, about a 240-pound linebacker, or one of the big bruising running backs, so not a scat back, but one of the big guys, running with a speed of 3.6 meters per second? Manny, since this is football, what's this question asking me to find, my friend? Oh, momentum, we have our new equation. Momentum is what times what, folks? Mass times velocity. It's going to be 112 mass times 3.6. And 3.6 meters per second? Yeah, that's not really well, 10 meters a second is like Usain Bolt fast because he runs 100 meters in about 10 seconds. So this is about half as fast. This is a big lumbering fullback, not going very fast, but hard to bring down because he's so big. 112, 3.6, 403, 0.2, 403. In terms of tackling, Manny, something that has around 500 or 600 kilogram meters per second of momentum, it's going to hurt a little bit to bring it down. Because you've got to get rid of its momentum, because when you bring it down, what's its final momentum going to be? Think about it. What's its final velocity going to be when you tackle him? So what's its final momentum going to be when you tackle him? Somehow you got to cancel that out. How? B says, what impulse must a tackler impart to the football player to bring him to a stop? Now, in our simplest case, we're going to assume this is straight head-on. In Physics 12, we'll look at, for example, ice hockey body checks where you hit somebody at an angle. That's much more difficult. Or curling, where you have collisions and they bounce off of each other at angles, much more difficult. This year, everything's going to be nice and in a straight line. The worst we're going to have to do is let to the right be positive, to the left be negative. So, oh, Manny, what's this question B asking me to find? B, read to me. Oh, what? What's another word for impulse? Okay, so it wants me to find that. Now, I got two equations. I have one that has forces and times. I have one that has masses and velocities. Which one am I going to use in this question? Masses and velocities. I don't see forces and times. In fact, part C is asking me to find the force, which also suggests I better use a different method right now. So I'm going to use the mv final minus mv initial. Darian, the mass times change in velocity. Hey, what did we just say the final velocity is? So what's the final momentum? What did we just say the final velocity is? 0. So what's the final momentum? Yoink. The impulse that this football player has to pass on, that this tackler has to pass on to the runner, is negative 112 times 3.6. And I hope none of you reached for your calculator. I hope all of you said, hey, that's the same answer as part A, but negative. Yeah. Because, Manny, what we're really saying is this. When all is said and done, when you wrap your arms around the person you're tackling, if both of you come to a stop, what do we want the final momentum of both of you to be? 0, which means if I'm starting out with 403 kilogram meters per second, I better add negative 403 kilogram meters per second of momentum to end up with a momentum of 0. Now, there's two ways I can do that, by the way. If I'm lighter, if I don't weigh that much, I better be moving faster, right? Or if I'm a big lineman who weighs twice as much, this is why the defensive lineman can stop those guys even though they don't move very fast. They're capable of passing on the requisite impulse. And now we're already, just this is starting to help figure out why certain positions in football are the size and mass that they are. Because of the physics. Have to be. Oh, if the tackle was completed in 0.8 seconds, what average force did the tackler exert on the other player? What are they asking me to find here? What did I just find in part B? Impulse? Hey, there wouldn't by chance be an equation that has force and impulse in it. Is there? There might be. Force, change in time, equals impulse. Shaq, how would I get the F by itself? Because you're a football guy too, so you should know some of this. Now, before we go further, what if, Shaq, the tackle doesn't last as long? What if time is smaller? What's going to happen to the force? Bigger, smaller, or stays the same? Think about it. Huh? Faster hits require you to hit him harder. What if you tackle him over 1 second? A long time. You don't have to hit him as hard because you're dragging him down slowly. That's why it doesn't hurt so much to bring a guy down over 5 yards, because it takes longer. That's why it hurts way more, Jeff, to bring a guy down in a half yard, one space closer. Now, I asked what average force did the tackler exert on the player. So this is true. The tackler is hitting the player this hard, but wait a minute. Forces come in what? You're going to feel the same thing. The only hope is maybe you're prepared for it and can tense up and deal with it. But those defensive guys, when they're hitting the wide receivers, they're receiving the same force back, which is why you will often see a defensive player after a big hit also not get up. Right? You've noticed this, I hope. I think playing football, yes? Okay, so now this is why. What was it? Negative 403.2 divided by 0.8. And again, you guys have just figured this out playing sports, but what I'm telling you is this is why that's the case for those of you that are football players, okay? Units, it's a force. Newtons. Sorry? Oh, negative. Why negative? Because the force is being applied in the opposite direction that the initial runner was going. Oh yeah, which makes sense. If I'm going to bring somebody to stop, I got to hit him head on. If you're tackling someone from the side at an angle, we don't have the math physics skills to handle that right now. We need something called vectors, and the math gets pretty ugly. Cool, because those are more realistic, but ugly. Hey, if I'm a football player in the NFL, how can I make it easier to tackle someone? Get fat. Again, that's why all those defensive linemen have those big bellies. If they can put on some pounds without sacrificing their speed, well, now it's easier for me to cancel out a guy's momentum. Oh, okay, if it starts to affect my speed, there's clearly a balance. You don't want to be 500 pounds and not be able to move out there because the guy will just go around you. So it's a balance, but again, this is why football players at the various positions look the way they do. Although we solved the previous problem using impulse, we really could have done it using Newton's second law. We could have actually gone, I know V final, I know V initial, I know time from part C, I can find A. And then now that I know A, I could go F equals MA. Why didn't we? Well, the main reason is, first of all, momentum is a very good tool for analyzing collisions. But it can also explain some other situations. Consider the following. Two eggs, identical eggs, are dropped from the same height, h. One hits a concrete floor and breaks. The other lands in a pail of water and survives. What's the main reason the egg survives? First of all, do they both have the same mass? Yes. Do they both have the same V initial? 0. Will they both have the same V final? Yep. So here's the issue. Write this down. Both have the same change in momentum. They both have the same change in momentum. So, wait a minute, what's another way to write change in momentum? What's another equation that had this in it? And Valoria, you were right, but I'm going to see if we can actually use physics words. So, what did you say the pail does? Okay, if time gets bigger and we both have the same change in momentum, what must be getting smaller on the right-hand side if time is getting bigger? Ah, if that gets bigger, that gets smaller. In fact, I have to beat somebody. We'll pause the video for a second. So impulse allows us to explain why you can have some changes in velocity and survive just fine, and undergo that same change in velocity and have damage. And it's because of, well, let's call this situation A, situation, hello. Try that again, Mr. Dueck. Vanish, vanish. Let's call this situation A, situation B. So situation A, situation B. In both of them, the change in momentum is force times time. But Valoria, in situation A, little time means huge force. In situation B, big time means little force. How many of you have ever played catch with a water balloon or a raw egg? How do you catch it? Think about what you were what were you really doing when you caught it? When you do that, what variable are you changing? You're lengthening the time of impact. You figured that out at age 6 or 7, whatever. The first time you did that, you clued in, I can't just catch this thing or I'm going to get soaked or messy. Here's another way to think about it. Why do they use bales of hay to line some racetracks? What's the advantage in being brought to a stop by a bale of hay instead of a brick wall? Same idea. Because you're stuck with the same change in momentum, well, we can change the time of impact, which means the force, and it's the force that kills you in a car accident. So I fibbed a bit here when I did this chart and we talked about ouch, injury, and death. All of you have gone through a change in momentum of 30,000 kilogram meters per second. You just did it over 5 or 10 minutes going from the freeway slowly to your subdivision, to your house, to your home, to slowly stop. Really, it's how fast you're having to undergo that.